Hey friends, welcome to the YouTube channel all about electronics. So in this video, we will learn about the cascode amplifier. So as shown in the figure, the cascode configuration is the combination of the two MOSFET stages. The lower transistor is known as the amplifying transistor and this transistor is configured in the common source configuration. And the upper transistor is known as the cascode transistor. So here the fixed DC voltage is applied at the gate terminal, but for the AC signal perspective, this gate terminal will act as a ground and hence it is configured in the common gate configuration. So in this configuration, the output of this common source stage is fed to the common gate stage and the overall output is measured at the drain terminal of this common gate stage. Now here, for a time being, this load is not shown. But this load could be a passive resistive load or it could be an active load like a current source. But anyway, this configuration provides a high output resistance, high intrinsic gain and the large bandwidth. So first of all, let us understand the reason or the motivation for learning this configuration. Now in the previous video, we have seen that the intrinsic gain of this common source amplifier can be given as Gm times R0, right? Where this R0 is the output resistance of this MOSFET. So we have seen that typically in the ICs, the achievable intrinsic gain is in the range of 20 to 50 and that gain is achievable only if it is biased with the ideal current source. In case of the actual current source, it has a finite output resistance and because of that, this voltage gain will further reduce. So if we want to achieve the higher intrinsic gain, then this output resistance needs to be improved and the cascode configuration exactly does that. So let's say the R0 is the output resistance of this common source stage. So in this cascode configuration, this common gate stage multiplies the output resistance by some factor K and hence it also increases the intrinsic gain. So let us understand this thing through a small signal analysis. So for the AC analysis, these DC voltage sources will act as a 0. And if we replace the MOSFET by a small signal model, then the small signal equivalent circuit will look like this. So to find the output impedance which is seen from this side or in the small signal equivalent circuit from this side, let us apply a test voltage considering all the independent sources in the circuit as 0 and let us find this test current. So the ratio of this test voltage to the test current will gives us the output impedance and this output impedance will be the output impedance of this cascode stage. Now here, once the input signal is considered as 0, then this voltage VGS1 will become 0 and because of that this dependent current source will also become 0 and because of that it will act as an open circuit. So if we see the equivalent circuit, then it will look like this. So here let's say this current is equal to Ix. That means the current which is entering the drain terminal is equal to Ix and the same current should also leave through the source terminal of this first MOSFET. That means the same current should also enter into this drain terminal. That means the current through this R01 is equal to Ix. Now let's say the current through this R02 is equal to I. So if we apply the KCL at this node, then we can write current Ix is equal to I plus ID2, or we can say that this current I is equal to Ix minus Gm2 times VGS2. So now let us apply the KVL equation in this loop. So applying the KVL equation, we can write this voltage Vx that is equal to I times R02, that is the voltage drop across this R02 plus Ix times R01, that is this voltage. Or we can say that this voltage Vx is equal to Ix minus Gm2 times VGS2 times R02 plus Ix times R01. Now here this VGS2 is the voltage between the gate and the source terminal of this second MOSFET, and for the second MOSFET the source terminal is connected to the drain terminal of the first MOSFET, and the source terminal of this first MOSFET is connected to the ground terminal. So we can say that this voltage VGS2 is actually appearing between the source and the drain terminal of this first MOSFET. That means this voltage VGS2 is equal to minus VDS1, and this voltage is equal to minus Ix times R01. That means we can replace this voltage VGS2 by minus Ix times R01. That means we can write this expression as Vx is equal to Ix plus Gm2 times Ix times R01 times R02 plus Ix times R01, or we can say that this Vx is equal to Ix times R02 plus Ix times R01 plus Ix times R01 R02 times Gm2, or we can say that this Vx divided by Ix, or this output impedance, is equal to R01 plus R02 plus Gm2 times R02 times R01. Now here this last term will be definitely larger than the first two terms. Let's say this Gm2 is equal to 0.1 millisiemens and this R02 is equal to 100 kilo ohm. That means this Gm2 times R02 will be equal to 10. That means this entire term is equal to 10 times R01. So approximately we can say that this Vx divided by Ix, or this output impedance, is approximately equal to Gm2 times R02 times R01. And if you observe over here, then this Gm2 times R02 is the intrinsic gain of this second MOSFET. So we can say that this common gate stage amplifies the output resistance of this amplifying stage by its own intrinsic gain, and therefore the output impedance which is seen from this side is approximately equal to Gm2 times R02 times R01. So in this way we found the output impedance of this cascode stage. Similarly, let us find the voltage gain. So in this case, by finding the transconductance of this overall cascode stage, we can easily find the voltage gain. So here, first of all, we will find the transconductance of this overall cascode stage, and then after, by multiplying it with the output resistance of this cascode stage, we will find the voltage gain. So first of all, let us understand this concept. Now the transconductance of the overall amplifier stage represents the change in the output current due to the change in the input signal, or mathematically we can say that this transconductance Gm is equal to I0 divided by Vi. Now here, to distinguish it from the MOSFET transconductance, it is represented as the capital Gm. So to find this transconductance, we can connect the output to the ground and we can find this output current, and the ratio of this I0 and the Vi will give us the transconductance of this amplifier system. Similarly, to find the output resistance of this amplifier, we can consider this input as 0 and we can apply a test voltage at the output side, and the ratio of this test voltage to the test current will give us the output resistance. And in fact, we already found the output resistance of this cascode stage. So once we find this output resistance and the transconductance of this overall amplifier system, then the equivalent output stage of this amplifier can be represented like this. So here this output voltage Vout is equal to minus I0 times R0, or we can say that it is equal to minus Gm times Vi times R0. That means Vout divided by Vi, or the voltage gain of this amplifier, is equal to minus Gm times R0. So here for the cascode stage, we already know this output resistance. So to find the voltage gain, the only thing which we need to find is the transconductance. Now here, to find this transconductance, let us connect the drain terminal of the second MOSFET to the ground terminal. So in this way, the output of this amplifier stage will get connected to the ground terminal. So with this, if we see the equivalent circuit, then it will look like this. And here, let us find this current I0. So here, this current I0 is entering into the drain terminal. That means the same current should also come out of this source terminal. That means this current should also be equal to I0, right? Now here, since the drain terminal of this upper transistor is connected to the ground terminal, so we can say that this VDS2 or this voltage is equal to VGS2. Similarly, the source terminal of this upper transistor is connected to the drain terminal of this lower transistor, and the source terminal of this lower transistor is connected to the ground terminal. That means this voltage VGS2 will appear between the source and the drain terminal of this second MOSFET, or we can say that this voltage VDS1, that is this voltage, is equal to minus VGS2. Now here, if we apply the KCL at this node, then we can write this current I0 is equal to this ID2 plus VDS2 divided by R02, or we can say that this I0 is equal to GM2 times VGS2 plus VGS2 divided by R02. Let's say this is the equation number 1. Similarly, if we apply the KCL at this node, then we can write current I0 is equal to GM1 times VGS1 plus VDS1 divided by R01, or we can say that it is equal to GM1 times VGS1 minus VGS2 divided by R01. That means I0 is equal to GM1 times Vin minus VGS2 divided by R01. Let's call this equation as equation number 2. So now, comparing this equation number 2 and 1, we can write GM1 times Vi, that is equal to VGS2 times GM2 plus VGS2 divided by R02 plus VGS2 divided by R01, or we can say that GM1 times Vin, that is equal to VGS2 times GM2 plus 1 over R02 plus 1 over R01. Now typically this first term will be much greater than the last two terms. So approximately we can say that this GM1 times Vin is equal to GM2 times VGS2. Let's call this equation as equation number 3. Now once again, let us write down this first equation. So the first equation was this I0 is equal to GM2 times VGS2 plus VGS2 divided by R02, or we can say that it is equal to VGS2 times GM2 plus 1 over R02. Now once again, this first term will be greater than the second term. So approximately we can say that this I0 is equal to VGS2 times GM2. And from the third equation, this GM2 times VGS2 is approximately equal to GM1 times Vin. So we can say that this I0 is approximately equal to GM1 times Vin. And therefore, this overall transconductance GM, that is I0 divided by Vi, is approximately equal to GM1. That means the overall transconductance of this cascode amplifier is approximately equal to GM1. So once we know the transconductance, then we can easily find the voltage gain. So as I said, this voltage gain AV will be equal to GM times R0, or in this case, this Gm is equal to Gm1 and this R0 is equal to Gm2 times R0 2 times R0 1. That means the overall voltage gain of this cascode amplifier is equal to Gm1 times Gm2 times R0 2 times R0 1. So this is the overall voltage gain of this cascode amplifier. Now here let's say this Gm1 is equal to Gm2. Let's call it as Gm, and this R01 is equal to R02. Let's call it as R0. Then this overall voltage gain of this cascode amplifier will be approximately equal to Gm times R0 whole square. And this gain is much greater than the intrinsic gain of the common source amplifier. So as you can see, there is a significant improvement in the intrinsic gain. So now let's see with the load how this voltage gain will get affected. And first of all, let us find the voltage gain of this cascode amplifier with the resistive load. So with the resistive load, if we see the output equivalent circuit, then it will look like this. That means this resistor RD will appear in parallel with the output resistance. So in this case, this voltage gain will be equal to Gm times this R0 parallel RD, where this R0 is the output impedance of this cascode stage. And now we know that this R0 is much greater than RD. That means this overall voltage gain is approximately equal to Gm times RD. And in this case, this Gm is equal to Gm1. That means we can say that the overall voltage gain will be equal to Gm1 times RD. And in fact, this gain is similar to the gain of the common source amplifier. So to improve this gain, instead of this resistive load, the active load should be used. So if we use the ideal current source as a load, then for the AC analysis, this current source will act as a open circuit. And in this case, the voltage gain will be equal to Gm times R0, or we can say that it is equal to Gm1 times R0, where this R0 is the output impedance of this cascode stage. So with the ideal current source, the voltage gain of the amplifier will be equal to the intrinsic gain. But if we see the actual current source, then it has some finite output resistance. And in that case, during the AC analysis, this current source can be replaced by the output resistance. So let's say this output resistance is equal to R02. So with this, if we see the output equivalent circuit, then it will look like this. And therefore, the voltage gain will be equal to Gm times this R01 in parallel with R02. Or we can say that it is equal to Gm1 times R01 in parallel with R02, where this R01 is the output impedance of this cascode stage and this R02 is the output resistance of this current source. So to get the maximum gain, this R02 should be comparable to the R01. So suppose if this P-type MOSFET is used as a current source, then in the AC equivalent circuit, it can be replaced by its output resistance. And in fact, in the previous video, we have already discussed it in detail. So in that case, if we see the output equivalent circuit, then it will look like this. So in this case, this voltage gain will be equal to Gm1 times this R01 in parallel with R02, where this R02 is the output impedance of this PMOS. So here, obviously, this R01 will be much greater than the R02, because this R01 is the output impedance of this cascode stage. So therefore, we can say that approximately this voltage gain is equal to Gm1 times R02, which is typically similar to the intrinsic gain of this common source amplifier. But this gain can be improved further by using the cascode current source. So now let us find the voltage gain of this cascode amplifier when the cascode current source is used as an active load. So this is the typical cascode current source. And here, this end, will get connected to the cascode amplifier. So first of all, let us find the output impedance of this cascode current source, that is the equivalent impedance which is seen from this side. So to find that, for the AC analysis, all the DC sources in the circuit will act as a 0. And let's say these two transistors are N3 and M4 respectively. So for the M4, if you see, the source and the gate terminal both are connected to the ground terminal. So if we see the equivalent impedance from this drain side, then it is equal to the output resistance of this M4. Let's call it as a R04. And here this second transistor will act as a cascode amplifier. So it will multiply the output resistance of this M4 by its intrinsic gain. That means if we see the equivalent impedance from this side, then it will be equal to this R03 times GM3 times R04, where this GM3 and the R03 are the transconductance and the output resistance of this M3. And as you can see, it is significantly greater than the single PMOS transistor. So let's call this resistance as R0P. So now let us connect this cascode current source as a load to this cascode amplifier. So here these VB4, VB3 and the VB2 are the biasing voltages. So here the input is applied at this amplifier transistor M1, and of course some DC biasing voltage VB1 will also be applied at the M1. Now for the AC analysis, all these DC biasing voltages will act as a 0, and we can replace this cascode current source by its equivalent output resistance. Let's call it as a ROP. So with that, if we see the output equivalent circuit of this cascode amplifier, then it will look like this. And in this case, this overall voltage gain is approximately equal to GM1 times this RON in parallel with ROP, where this RON is the equivalent impedance of this cascode stage and this ROP is the equivalent impedance of this cascode current source. Now if this RON and the ROP are equal, then the overall voltage gain will be equal to GM1 times this RON divided by 2, or we can say that it is equal to GM1 times GM2 times R02 times R01 divided by 2. Now if this GM1 and the GM2 are equal and this R02 and the R01 are equal, then this overall voltage gain will be equal to GM times R0 whole square divided by 2, which is significantly higher than the gain of the common source amplifier with the active load. So using this cascode amplifier along with the cascode current source, the voltage gain can be improved significantly. So I hope in this video you understood how the cascode configuration improves the output resistance and the voltage gain. Now this configuration also improves the bandwidth, but we will talk more about it during the frequency analysis of the amplifier. So that's it for this video, and if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.